Hey everybody, it's Doc here again. We're on day 2, Calc1, Lesson 6, Section 6, or 2-3 if you have the other book, which again, I don't suggest. But anyway, let's take a look at the limit laws. Now, I'm not going to spend a whole lot of time going through each and every one of these because I think by looking at them, you can see pretty much common sense. This says that you can add two functions first, then take the limit, or you can take the limit of each of them separately and then add those limits. Same with subtraction. Here, this one is handy. You can either multiply a constant through the function first and then take the limit, or this is usually easier, or you can take the limit of the function and then multiply by your constant. Multiplication, same thing. You can multiply them both together first and then multiply them both together first and then take the limit. Or you can multiply the limits together. Division, you can divide first, take the limit, or take the limit and then divide. And of course with division, we have to make sure that the denominator is not 0. So, verbally stated as follows: limit of a sum is the sum of the limits. Limit of a difference is the difference of the limits. Limit of a constant times the function is the constant times the limit. And the limit of a product is the product of the limits. Limit of the quotient of the limits, or limit of the quotient is the quotient of the limits. And remembering the denominator can't be 0. So I'm going to skip example 1. And we're going to go on to the other laws that I want to cover. This one, this is also one that's quite handy. You can either take the function to the nth power and then take the limit, or you can take the limit and then take it to the nth power. So you can imagine if you had a function and it was to even the 10th power, how difficult it might be to take that polynomial to the 10th power and then find the limit. Whereas you can just find the limit of the polynomial and then raise it to the 10th power. So this is handy as well. Now if you have a constant, the limit of a constant is just that constant. And the limit of x as it approaches a is just a. Now, this one right here is going to come today to show us something that we can do that's much easier than what we looked at a little bit ago. Similarly, 9 says if I have x to the n, and as it approaches a, I can just put a in and take a to the n. Now, where n is a positive integer, important. All right, also, if we have a root function, the nth root of x, as x approaches a, I can substitute a in and just take the nth root. And then the last one we'll look at today, as far as these rules, we have the nth root of f of x as x approaches a. We can do that first and then take the limit, or we can take the limit and then do that. So again, these are so that you can go through and manipulate your problem so you can make it a little bit easier. Now, example 2, I'm not going to go through. We're just going to take a quick look at it. What it does is it just takes the properties that we looked at before. Here is the limit of a polynomial. They're showing you that you can break down each one, find the limit, and then combine it. Same with the bottom down here, doing the same thing. So you can look at that on your own. But the key part of this section right here is now discovering that we have direct substitution and certain limits. If f is a polynomial or a rational function and a is in the domain, okay, so very key. A has to be in the domain of f. Then the limit as x approaches a of f is equal to f of a. What? What does that mean? That means I can just take whatever this is, plug it in for x, and get my limit. So we're going to take a look at this today. Okay, example 3. We have the limit as x approaches 1. We have x squared minus 1 all over x minus 1. Now, we take a look at this and we say, well, wait a minute. You know, you said that you can plug 1 in for x. If I do that, I get 0 here in my denominator. And that's a problem. And you're right, that is a problem. But what I didn't tell you before is that you can simplify this rational expression first. So what we have to do is we take a look at the top and we say, does it factor? And it certainly does. And now we notice that we have quantities that reduce. Don't say cancel, it's reduce. Okay, so reduce. Now, after I reduce those quantities, I now have the limit as x approaches 1 of what's left, which is x plus 1. And now when I substitute that in, I'm simply going to get 1 plus 1, and that is 2. And that is my limit at this point. So this is the problem that we looked at back in a couple sections ago when we were trying to find the slope at 0.11, and we found the slope to be, we estimated it as 2. So this is how we can do it now. Much easier way, as you can see. We don't have to use a table. Sometimes you do have to use the table, but most of the time you can use direct substitution. Okay, let's take a look at the next property they have here before we go on. Now let's see what they have to say in this note. All right, note, in example 3, we were able to compute the limit by replacing the given function right here by a simpler function, that's what we did, with the same limit. This is valid because f of x equals g of x except when x is equal to 1. Now remember, we are still finding the limit. So we're still saying as it approaches 1. We're not saying at 1. So we don't consider what happens actually equal to 1. So don't lose sight of that, okay? In general, we have to follow the useful fact that we have f of x. We might be able to reduce it into another function called g of x. And when x is not equal to a, we can find the limit by plugging in our value by direct substitution. Okay? All right, let's take a look at this example 4. It's a short example, so we'll look at it right here on the book. We have a nice graph. Okay, let's look at this limit. This is a piecewise function. It says when x is not equal to 1, you can use this. But when x is equal to 1, the answer is pi. So we can see over here that the graph looks like this. Here it is, x plus 1, but when we get to 1, the result is pi. So, again, this is just to emphasize that we're not looking at the value at pi. We're looking at as it approaches pi. Okay, so since g of x is x plus 1, for x does not equal 1, then we have the limit. Then we can say limit and then plug 1 in. But we have to put this here. We can't just say, oh, we're finding the coordinate and plugging it in. Okay, so there's a difference. All right, example 5. Three plus h quantity squared minus 9 over h. Here, I should move that over. Again, I don't like to use a pen. Limit as h approaches 0. limit as h approaches 0. Obviously, we look at this and say, I can't substitute 0 directly into here because it's on the bottom. But let's multiply this out and see if I can simplify it in some way. This is a binomial square. And as I said before, binomial square, you should be able just to multiply it out by realizing that you have 3 squared, then you have the h squared, and then the middle term, you multiply them together and double it, so that'll be 6h. This sign is the first sign, and the last sign is always positive. Okay? So that minus 9 all over h. Well, now I see here that my 9's will cancel. Now you say cancel when you're getting rid of something. So we have 6h plus h squared all over h. So I'm going to factor an h out. And now I can reduce my h. So now I have a much simpler, the limit as h approaches 0 of 6 plus h. And now I can plug my 0 in. And when I plug my 0 in, I will get 6. Okay? Questions there? If you have any questions, you know what to do. Text me, email me, give me a call even. All right, example 6. All right, example 6. So I have the limit as t approaches 0, square root t squared plus 9 minus 3 all over t squared. Okay. Now I'm looking at this saying, well, I can't plug my 0 into my equation. And I don't really see any way that I can simplify it. However, you have to remember, just as with any fraction, for instance, let's go over to our little thought bubble. If I pick any fraction, we'll just do 1/2. And I decide I want to change the way it looks and keep the value. I can do that by multiplying it by any value of 1 that I want to. So let's say I just decide I want to multiply it by 5 over 5. I get 5/10. Well, this is still the same value as this, but it looks different. Same kind of concept here. I can multiply this by a value of 1 so that I can maybe simplify it a little better. And I see that I have something minus 3 up here. If I multiply it by, see if you remember this word, its conjugate, t squared plus 9 plus 3 over square root of t squared plus 9 plus 3, that is a form of 1. And why would I multiply it by that? Well, I would multiply by that because if I do that, this is a difference of squares. And I realize that that might help simplify things a little bit better. But let's see if it does. Okay, so now when I have a difference of squares, I square this. I get t squared plus 9. My middle terms will cancel. And then I have minus 9. Well, that made the top a lot better. Okay. So on the bottom, I have t squared. And then I have still my square root of t squared plus 9 plus 3. Not too bad. Okay, it's actually not going to take as much room as I thought. All right, so now let's reduce this down. On the top, I just have t squared. On the bottom, I still have the same thing. So t squared, you can see what's going to happen here. T squared plus 9 plus 3. Okay, reduce, reduce. This becomes a 1 at the top. So now I have 1 over t squared plus 9 plus 3. This is square root, sorry. Okay, put square root there. Don't want to forget that. All right, so now let's see. If I have the limit as t approaches 0 of this, can I put 0 into that function without getting 0 in the denominator? And I can. So that makes me happy. So if I put 0 in here, I now have 1 over, put 0 in for t squared, the square root of 9 plus 3. And that will be 1 over 3 plus 3, which is 1/6. Not bad at all. Okay, so the limit as t approaches 0 of this function is 1/6. Okay, now this should also look familiar because it was back a couple sections ago. We did a problem like this when we looked at it, and this does confirm that our answer that we got of 1/6 there is in fact the limit. All right, we have a theorem to look at quickly before we go on to the next example. The limit of a function as x approaches a will be L if and only if. This means it absolutely has to happen. If and only if. Both ways. If the limit as it approaches from the left is L and the limit as it approaches from the right is also L. Okay? When this is the case, then we have a limit. We looked at that before. So let's do another example. Example 7. Okay, we have the limit as x approaches 0, the absolute value of x equals 0. So, now recall that when we looked at, I'm going to go ahead and put the book back up here so we can look at the graph. This is our absolute value function. Here's the piecewise function to remind us of what it looks like, this and this. So, if I take a look at this from the left, as it approaches from the left, what is my limit as we approach 0 from the left? It is 0. Let's look at it from the right. As it approaches from the right, what is the limit? It is 0. So by the theorem, we can say that the limit of the absolute value of x as x approaches 0 is also 0. Not a whole lot of work to do there. So just observing the graph, seeing that it's the same on both sides. Now, example 8 is a little bit different. We looked at this example also before. We have the absolute value of x over x. We want to prove that as x approaches 0, this doesn't exist. So let's look at it coming from the left. As we come from the left, we see that we get a value of, oh, I'm sorry, it comes from the right first up here. As it comes from the positive side, the right, we see that we get a value of 1. As it comes from the left, we see we get a value of -1. Since these two are different, then we do not have a limit. Okay? Since they're different, we don't have a limit. All right, let's look at example 9. Looks like it's a similar one. Look at it by observation more so. So now we want to see if this has a limit as it approaches 4. And we're using 4 because that's the number here. So determine whether the limit as x approaches 4 of f of x exists. Let's take a look. Okay, if we come in from the right or the positive side, and coming in from the right, we look at the limit as it approaches 4 And we say that we can put 4 in here because we're looking for the limit, and we get 0. If we look at it from the left or the negative side, if we look at it from the left, then we'll have the limit as x approaches 4, 8 minus 2x. We plug in our 4 here, and we also get 0. Since our right hand equals our left hand, then the limit does in fact exist. The limit of x as it approaches 4 of f of x is 0. And the graph shows this right here. Okay? All right, now we have greatest integer function. Greatest integer function is the one that looks like steps. Okay, so now we're going to look at the greatest integer function. So we have the largest integer less than or equal to x. So largest integer less than that number. So the largest integer less than or equal to 4 is 4. The largest integer less than or equal to 8, or contained in this, we can say, is 4. The largest integer that is less than or equal to pi is 3. The largest integer less than or equal to square root of 2 is 1. Now, again, keep in mind that we're looking at the largest integer that is smaller than negative 1/2. The largest integer that is smaller than negative 1/2. So that would be negative 1. Okay? So now we want to show that the limit as x approaches 3 of this greatest integer function doesn't exist. So we're going to go over here at 3. This is what we're taking a look at right here. We're going to approach it from the negative side and the positive side, from the left and from the right. And when we look at it from the right, we see that our value, as we approach it from the right, our value is 3. As we approach it from the left, the negative side, our value is 2. So since these two are not the same, then by theorem 1 we say the limit does not exist. Now, another theorem. If you have a function and it's smaller than or equal to another function when x is near a, except at the possibility at a, because remember with limits we're not looking at the exact value of a, and the limit of f and g both exist as x approaches a, then the limit of that first function is also going to be smaller than the limit of the second function. Okay? And this leads us to what's called the squeeze theorem. So the squeeze theorem, if you have a function g of x and you're looking for it, and you have f of x on this side, and you have h of x on this side, when x is near a, then what you realize is if this function, we'll say the limit is 10. If this function's limit is 10 and this function's limit is 10, then the function in the middle's limit also must be 10. Okay? So here we say if as x approaches a of f of x, if that's equal to the h of x, these are both 10, we'll say, can be any limit that we're looking at, then we can conclude that the limit as x approaches a of g of x is also 10. Okay, so here's a graph example of that. We have h here, we have f here, here's our a value, we're looking for the limit, we find out that the limit of both of these are the same. We know that this has to be in the middle of them, so it also must be the same. Okay? All right, example 11. Example 11, we're going to show that as x approaches 0, x squared sine 1 over x equals 0. First, we know that we cannot use the limit of x squared sine 1 over x as the limit x squared times the limit x approaches 0 of sine 1 over x. Because the limit of sine 1 over x does not exist. So instead, we have to apply the squeeze theorem. So we need to find a function of f smaller than x squared sine 1 over x and a function bigger than it so that we can squeeze it together to see if it's the same. All right, let's see if we can do that. Okay, we know that the sign of any number lies by itself. Sign of any number lies between -1 and 1. Our range. And an inequality remains true when multiplied by a positive number. So we know that if we have x squared greater than 0 for all x, then multiplying each side of the inequality, we should get negative x squared on this side and x squared on this side should be on each side of x squared sine 1 over x. Here's the crazy graph. So what we can do is look at, by the squeeze theorem, we have a parabola here, x squared, we have a parabola here, and we want to find this value here, and this is in between the two of these. By the squeeze theorem, we can in fact say that the limit as x approaches 0 of x squared sine 1 over x is 0. Okay? All right, well, that is the end of section 1-6. And as always, you can text, email, put some comments, and I will get back to you. See you at the next lesson.